Hello and welcome to this Sensor Data in the Cloud webinar. Today we'll quickly be going over a few things to do with getting your data out of your local machine and up into the cloud. So we're going to talk about where the data comes from, how you can access it locally, how you then get it into the cloud, and once it's up there, what do you do with it? So, where is the data? Well, at the moment it doesn't exist. It's stuck inside the sensors and we've not created it yet. Well, the best way to get the data created is to start putting a system together, and that's what we've done here. We've created a demo case which will enable us to show you exactly what's going on. Now, we at SIG, we understand that the steps into this digital future can be daunting. Is it the right time? Should we go for it now? Should we wait and see what happens? Or perhaps you've already started taking the first few steps. Who knows? Maybe you're halfway down the road already. Whatever stage you're at, we've got some solutions that can benefit you. And I've put together a demonstration case, as I say, that we can use to easily show you how to get to the data both locally and in the cloud for analytics and storage purposes. Inside the demo case are the following components. We've got a SIG200, which is our sensor gateway, which is in the middle of the box with all the cables plugged into it. We've got a TDC, which is the cloud connection in the top left corner. We've got a SIG100, which is a IO-Link enabled device that's connected to the SIG200, and it's the digital IO hub for inputs and outputs of ons and offs. An IMC30, which is an inductive sensor. An FTS, which is a flow and temperature sensor, you can see there with the long probe on it. And we've got an optical sensor, which is looking at a small reflector as part of the case as well. There's also a couple of digital input devices and output devices, as I say, connected to the SIG100. We'll briefly discuss the 200 and the TDC in a little bit more detail, as well as explaining the hidden data within an IO-Link sensor, and then we can show the case working in its local mode, and moving up and to the end game we'll start trying to get to something that looks like the image on the right, where we can see cloud-based data, something going on in the virtual realm that can actually prove very, very useful indeed. So, the SIG200. What is it? Well, it's a sensor integration gateway. That's what SIG stands for, and it allows us to connect IO-Link based devices and standard I/O as well on this device if you want to, in an easy and not expensive way. What are the benefits to you as a user? Well, you get to access data at the sensor level no matter where it is within the machine, because as long as it's connected to one of our IO-Link masters, you can access it via the network on the machine through the SIG200, so you'll never need to worry about getting access to the sensor information. Transparency from the sensor to the PLC and back again, which means we can easily send signals to and from the sensor. As I said a second ago, it is not an expensive entry to this type of solution. Basically, with one IO-Link sensor and a SIG200, you can make a start on your digital journey and start extracting useful information. Setup is really straightforward because we've got the onboard web server. That makes setup really quick and easy. You can see what's going on with your sensor in terms of process data and also service or parameter data. That's the hidden information inside the sensor. We've also got logic on board on both the SIG200 and actually on the SIG100. That means you can do some localized computing within the SIG itself. That means you can take some of the load off your PLC and effectively do some edge-based computing, which is basically the edge of the system. We've also got an onboard REST API here, which means communicating with this device and the devices connected to it is very straightforward using a REST client, which, for example, the TDC has on board, and we've also got some software that we can use to mimic that and to show that, which we'll get over to in a few minutes. So the TDC, think about your data, analyze it and act upon it. What is it? It's a telematic data collector. Alright, it's a big mouthful. It's basically a cloud gateway which takes all the information from the system, it squeezes it all into one place, manipulates it, organizes it, and then sends it wherever you need it to go, whether that be a local dashboard, whether that be into some local storage or a cloud storage, or for cloud analytics or dashboard use using protocols such as MQTT, OPC UA. We've also got Ethernet on board, we've got Wi-Fi, and you can also fit a SIM card, so you've got localized data monitoring even if your asset is mobile. So what are the main benefits to you? So you've got event and sensor status logging in the cloud of your choice, for example AWS, the Amazon Web Services Cloud, or Google Cloud, Microsoft Azure. It forms the foundation for active and predictive maintenance because we've got the ability to use text messaging and emails from within the TDC or from within the cloud, depending on how you want to go about it. You've got user-defined real-time alerts, which utilize those communication methods, the text messaging and the email. Simple configuration, relatively speaking. It's not that hard to get your head around. There's no additional software, there's no additional licenses for this particular piece of hardware. All you would need to pay for on top of the hardware itself is the SIM card cost if you use one, or the cloud-based costs if you choose to use a cloud service. And it's also got onboard GPS, which could be very useful if, as I say, you've got a mobile asset such as an articulated lorry, or you've got very remote locations that you might want to make sure are being utilized properly. The hidden data. This is what we've been referring to a little bit earlier. Within a sensor, we've obviously got the ons and the offs. We've got measurement values, particularly in terms of distance or flow levels, things like that. But we've also got things like current receiver level, which is the amount of light that's getting back into a particular sensor. In this case, the WLA16 in the case. That's an optical sensor with a reflector. So we can see that we've got some excerpts here. The top bit of text is from the IODD file, and the bottom piece of text is from the documentation that you can download with the sensor. So what is an IODD file and what does it mean? It's an input-output device description file, and what it does for you, it contains all the indexes and all of the variables that are linked to those index numbers, and it allows the computer or the piece of hardware you're working with to interpret those and move them into a way of showing the information to you as a user that makes a lot of sense. It also means that we don't have to start working with numerical indexes, although we can. It's always a lot more straightforward to work with defined variables that are basically written in a language that we understand much more easily, such as English. Okay, how do I access the data for local use? So this is use within the machine that we're sitting on, and not necessarily the hidden data at this point in time, but certainly accessing the process data. And IO-Link does also enable additional process data to be created. For example, the IMC, the inductive, would normally, in a normal sensor, have one switched output, and that would be it. That's everything you're going to get, on or off. With the IMC 30 that we've got on this case, we've got the ability to have 4 digital outputs from one sensor, so 4 different levels of detection, and we've also got the ability to have an analog value based on the amount of metal in the field. So we're going to use that ability, and we're going to use it as a chain detection monitor. So what we can do is we can monitor the position of the chain relative to the sensor in this demo case, which is effectively a flow wrapper in a different format. So we've got a chain drive and we've got some products that want to be monitored on top of that, and we can take that value from the process data and we can interpret it with the logic and do something with it. So we go through the web server, we check the sensor configuration, we make sure it's all okay, that it's working properly, that it's detecting what we would like to detect, and once we're happy and we can see everything coming back, then we can go through the logic editor and we can make things happen. So within that logic editor, we're also going to inhibit the feedback from the IMC, and we're then going to be able to use the lamp as a product detection indicator from the optical sensor. So it's basically doing 2 jobs with the same lamp, and that's all enabled and controlled via the onboard logic of the SIG 100 and the SIG 200. They've both got their own onboard logic editors. The primary difference is that the SIG 200 has access to the IO-Link data of the sensors, the process data over IO-Link, which effectively means, as we've said, you've got analog values, whereas the SIG 100 is pretty much restricted to ons and offs. Over the next few minutes you'll see us referring to the use of a plastic slide or contamination, and you can see here in this short video what I'm referring to when we use it. It's a little plastic window and we can use it to represent dirt buildup on either the reflector or the sensor itself, and you can see that in the cloud there things change when we utilize this. So let's take a look at the web server and the logic editor as part of this process. So here is the SIG200 web server that's hosted on board the SIG200 itself, and you can see here this is the status window. We're going to quickly have a look at the configuration section, and you can see if we click on the IO link port button we will get an overview of what's going on within the system itself. And you can see that we've got different devices connected and labelled up on the system. We've got IODD files ready uploaded, all relevant to the devices that are connected to them, and the pin configuration is discussed here. Now we can click on the individual IO link devices themselves as well, so we'll do now. And here we can see the IMC on port S1. Let's just switch down to the W16 on port S4 though. And what we can see is that we have some process data being shown here, which is currently saying true because we can see the reflector on this device. If I put my hand in front of it, bit 0 goes to false, and then take my hand away, bit 0 goes to true, false, and true. So we can see there that we get process data coming in, but we also get the ability to read different things. So I'll bring those up now and then we'll be able to show you what they are. So you can see here, you can see the quality of run and the quality of alignment, and if we need to see that information we can easily bring that out. So what I'm going to do is pop a plastic sheet in front of the reflector, and if I quickly scroll back up and read all the device information again, you can see that the quality of run has dropped down to 67 here. Okay, and we'll do that again. I think it will have dropped down a little more, and down to 51. Now if I remove the plastic and allow that to come back up, you should see that we'll be able to see what's going on there. I can keep it on the same screen, so I'm going to read that back out. Quality of run 87, read it again. Quality of run 91, quality of run, go up again now. So this is acyclic data, so this is data that comes out as you request it. It's not constantly uploaded. It's entirely possible to make it something that can be requested again and again and again. This SIG200 does have a REST API on board, which means we can send commands over a REST API interface. We'll do a short demonstration of that in a moment using some software that can pretend to be a REST API client. So hopefully you'll be able to see now, this is our logic editor, and we can have up to 20 of these different individual blocks that we can drag down from up here and drop into the logic. Now I'm not going to do that right now, I'm just going to explain what's going on and how these things work. So for example here we've got the S1 analog value, so that's the value from port S1 that is the analog signal, which is the IMC, and what we're doing, we're comparing that in these three blocks here, and we're making sure that it's either above, below or in between certain values which are derived from the constants over on this side of the logic here. You can see that I'm just highlighted it in blue. Now depending on the output from these compare blocks here, we can then move that logic through and we can pass it down through various logical blocks, in this case a couple of ANDs, and we can send it via port S2 to input logic 1, which actually goes to the SIG100 and is processed within the SIG100 and then is used to flash the red or the green lamp depending on which one of these S2IL values we're using. So you can see it will either be S2IL1 or S2IL2, and that will be green or red respectively. If neither of the compares give us an output, then what we'll find is that the lamp will remain off and the SIG100 will take care of that. the logic's really easy to use and set up. I know it may not look it because of these wires interconnecting everything, but at the end of the day it's a drag and drop interface, and you can easily connect things together and make quite powerful but simple logical throughput and logical controls that can be taken care of. And you've seen that during the localized demo. So yeah, just to finalize this point really, so the output goes to S2IL1 or S2IL2, and we'll just flick to the SIG100 logic, and you can see here we have IL1 and IL2, which have been referred to by the SIG200 and connected accordingly. And through some internal logic on the SIG100, we effectively end up down here on the bottom right with output color 1 or output color 2, and that's effectively the green and the red lamp on the SIG100 that's connected to port S5. So hopefully that all makes sense. It does look a little bit busy, but honestly it's not that complicated. Thank you very much. Now we're going to show what can be done locally using the inductive sensor and the output lamp, as well as the optical sensor and the inhibit sensor. So as we've discussed, there's various features on the demo case itself which are localized to the case. So the first thing is, using the output lamp and the IMC inductive sensor, we can show the position of the chain. So we're going to use a metal target to pretend to be the chain, and if the chain is in what is perceived to be a good distance from the IMC or the inductive sensor, then we get a green lamp. If the chain drifts, so it's in the wrong position, comes closer to the chain or further away potentially, then we are outside that range and we get a red lamp. Back in range we get this situation here, and we can see the change there as I move it further and closer to the sensor. Now in addition to that, we've also got the ability to block that signal here using this background suppressed sensor, so you can see now no matter what I do we don't get an output here. And that might be useful for mode change or something like that. So at the moment we're monitoring the chain, but if I take that metal target away for a minute and block that off, I can still see the product count, which uses both lamps on the lamp in this particular demonstration to show that we can see different things going on with the same information. So within the SIG100 we've got different parts of the logic being used to show us what's going on in terms of the feedback from the lamp. Okay, so now we know about the data, we've seen it in local use, but I'd like to get it into the cloud. So how do we do that? Well, this is where the TDC really comes into its own. So far it's not done very much, but using some simple and extremely powerful onboard software, we can tell the device to do pretty much whatever we want. Now we're using containers on this device, so different containers can have totally different features. The one that we're mainly using today in this demo case is the Node-RED container. So we're going to be able to use REST API to communicate with the SIG200 from the TDC, which then means that we can not only communicate with the SIG200 itself, but also the devices that are connected to it. And we're also going to see that we're connected to two different clouds using the MQTT protocol. So in a moment we're going to see some more pre-recorded but as live video. It was recorded and narrated at the same time. You'll see that we're going to take you through the process and hopefully enlighten you as to what is possible with this little blue box. It's quite a simple looking piece of tech, but we'll just quickly go through here. For example, this is a Node-RED flow, part of a flow. The information travels from left to right, and ultimately we process each section of the data one at a time and pass the information on to the next node. Here's an example of the information you might find in the prepare request function. So that's the REST API information, which we'll see in a second in another video. This is the information you would find in the HTTP communication node here. So that's basically taking that REST API information and carrying it via the correct protocol HTTP and waiting for a response from the SIG200. And then this is the kind of information we would use to extract that data and put it wherever we need it. So in this case it's extracting the data, it's mapping it to a global variable, and it's also sending it up to the message topic, as you can see there, which is what the TDC cloud will use, and we'll talk about that in a little bit more detail. Okay, so let's get a clearer understanding of what we mean by REST API, how that works, and also the Node-RED container on the TDC. We'll go into that in a little bit more detail and cover it in a slightly more technical aspect. So in the logic video we said we'd refer quickly to the REST API. The software you can see on the screen is a REST API client called Insomnia, and at the top in the middle you can see the REST API command using the IP address of the SIG200 and some other bits of addressing information. What we're going to do, we're going to use the variable v current receiver level live, and we're going to speak to port S4, so it's going to be a post command, and all I'm going to do is I'm going to send that command to the SIG200, and I will get a value back here of 98 for the current receiver level, which is pretty much what we want, more or less 100%. Okay, so I've now popped the dirty film in front of the reflector, and if I now do another send, so again it's acyclic, so I'm going to send the request again, and I get a new receiver level live 72. Okay, 72. It should stay about that because it's a live level and nothing's really changing. However, the quality of run I can also read out. If I read that out now, 48. Now once I remove the film, I'm going to do a few quality of run reads and see what happens. So quality of run 59, quality of run 67, 75, 78, 81, 83, and so on and so on. And you can see that the quality of run is improving over time due to the algorithms that are taking care of calculating that value. So that's the REST API, and we can basically send those very same commands from the TDC directly into the SIG200 and communicate with the devices that are attached to it or with the SIG200 itself. And you'll see how we do that in another part of the video. So now we're inside the container on the TDC for Node-RED. So this is the Node-RED container, and you can see there's lots of different flows of information. This flow, for example, that I've just highlighted in the orange borders, is injected every few seconds, so it's every 5 seconds. So every 5 seconds we do that, and we can see that I'll just highlight the format data. So what we're doing, we are doing the REST API command, and we're getting a value out. And at the moment, it's showing me that the current receiver level is 98, and we can monitor this in this Node-RED interface. So I've put the piece of plastic in front of the reflector, and you can see the current receiver level drops. Now, in the one below it, the quality of run, you can see that that's also dropping, and that's going to be dropping a little bit further as the algorithm works out what the actual quality of run is right now, and it continues to drop. If I remove that plastic film, you'll see the current receiver level and the quality of run should start going up, but the quality of run will be a little bit behind because of the algorithms that calculate that value, whereas the current receiver level is a live value, more or less. There you go. You see it's going 98 on the receiver level, and then the quality of run is slowly tracking back up. So that's a way for us to access the information over a REST API, and then what we can do via an MQTT broker, which is hosted by the cloud, the TDC cloud in this particular case. If we have a look inside there, we've got an IP address, a port, there's some login information, security information, but what it basically does is form a secure connection whereby we can upload all of these bits of information to the TDC demonstration or development cloud, and we can then access each bit of that information within that cloud, and that will be shown in a few moments. However, we've also got another flow where we are accessing the data, all of the same data and a few other bits actually, and what we're doing then is we are taking that data and we are creating a message payload here which has got all of this information inside it, and what we're doing is we're sending it to the AWS cloud. So again, it's a different server address, but obviously this one's an AWS server. There's all the usual certificates that have to be put together for this and make sure that everything's secure. But then effectively that data goes into the AWS cloud. And we will refer briefly to an incoming test from the cloud. This broker here, this connection here, is actually connected to a digital button in the TDC cloud. And if I click that button in the cloud, then this little purple block will receive some information, and then it will do whatever comes after it in the flow. In this case, it's just a case of reporting through the debug window that we've received a click. So it's doing something, but it's not doing anything useful. So hopefully that's a brief introduction to Node-RED, or a short overview if you've already been made aware of what Node-RED is. There's quite a bit going on, but hopefully you'll get to see enough to understand that this is very, very powerful indeed, and we can do local edge computing in this area, in this platform, but we can also do more complicated cloud-based data analytics if we pass some of this data up into the relevant cloud space. Great, data's in the cloud, fantastic. Now what do we do with it? Well, as the commands such as MQTT are not cloud specific, we can send the data anywhere we want, and the examples that we're going to show in a moment are based on just two of the many possibilities that you've got open to you. Now we're going to show our development cloud, the SICK TDC cloud, where we can see quite a lot of cool stuff going on. But we're also going to show some information in the AWS platform. So that's something that's open to anybody to use, just as much as Azure or Google Cloud, anything like that. So you'll see in a second the TDC cloud. Then we're going to look at the AWS platform, and they're both going to be shown in, again, some pre-recorded embedded footage. And what you've got to understand here is once the data's in the cloud, really it's only your imagination that's stopping you. So what happens next is entirely up to you. So that's fantastic. Now let's go and take a look at what that information looks like in the cloud itself. So as we've discussed, we've also got cloud connectivity via this case. So what we'll do first of all, we will quickly pop the case into demo mode. So to do that, we just unscrew one of these caps and just cover this sensor here permanently. And what that does, after 10 seconds of being covered, this sensor will pop the case into demo mode. And as long as that remains covered, then it will start to do this nice little flashing light show. And what that also does is give us a count of how many, it's a virtual count of how many things the inductive sensor is detecting. So every time the lamp goes green, it increments the count by 1 for the IMC sensor, the inductive sensor. Now, if you look at the FTS temperature graph, I'm going to grasp the probe on the FTS, and you can see straight away, almost instantaneously, the temperature FTS temp 2 shown on the screen has started to rise quite significantly. Okay. So that's just showing you that this is real time, well, almost real time feedback. So we're mapping the values into the cloud right now. I'll let go of that. You can also see that the FTS is in a simulation mode, which is quite a useful feature actually. If you're building a wet rig, but you haven't got around to wetting it up yet, and you want to just test the electronics are functioning, you can put this in simulation mode, which is what we're actually doing here, and cycling through lots of different values for the flow, and you can see that in the FTS flow graph. You can also see now the IMC count, so the virtual count for the IMC, the inductive sensor, is now going up, and if I introduce a metallic target, you should see the large bar graph change state, and there you can see we've got a value being fed back, and you also see that the system is now classed as OK. It doesn't think there's a change snap. If we go a bit closer, we get a proximity warning. So we've got 3 states in the cloud here. We've got system OK, we've got proximity warning, and if the chain disappears altogether, we've got change snap, which you'll see come back in a second. There we go. Now, if we wanted to, we could initiate warnings, either text or email warnings, based on that proximity, if we chose to. So in addition to what we can see there, we've also got an additional dashboard. If I go to the service dashboard for this demo case, there we go. So what we can see here is various bits of information about the FTS on the left hand side of the screen. Things like how many times it's been powered up, what the supply voltage is to that device at any given moment, and we're tracking that. You can see that's all within a very, very tight range, but a nice little feedback graph nonetheless. And on the right hand side we've got stuff for the photoelectric sensor, the W16. So we can see the receiver level is up almost at 100%. If I cover that sensor, so we're detecting a product, you'll see the receiver level drops right down. Okay, now the quality of run hasn't changed there because I'm detecting a product. You don't want the quality of run to be reporting issues every time something like a product gets detected. Take my hand away and that'll be tracked and it'll go back up. Now what we've also got is a clear object or clear bit of poly, and what we're going to do, we're going to use this and we're going to pretend that it's dirt on the reflector or the lens of the photoelectric. We're going to pop that there in front of the reflector, and what you'll see is that the receiver level has dropped, but crucially the sensor's not actually detected it because it's not set up to do so. It's set up to detect solid objects like my hand. And now what you can see is the receiver level has dropped, but at the same time the quality of run has also started to drop, because what it's saying is that time after time after time as it's going through its internal processes, I'm not seeing the quality of signal back from the receiver that it should be. If we pop that out, so someone basically has had a warning now and they've been told to go and clean that sensor or that reflector, we'll take the contamination away, and what we'll see is that the receiver level will shoot back up and the quality of run starts to track as well. So the quality of run will always lag slightly because it's got an algorithm that calculates it. But we can see here, both on the line graph and also on the dial, at a glance we can see that everything's back in the green and we're running okay. Okay, so in addition to the windows we've already seen, here is another little window in the cloud, in the TDC development cloud that we have, that we're now comparing IMC Count 2, which we know is the virtual count from this case, but it could equally be live counts. If I take it out of demo mode, I can literally physically trigger the IMC sensor, which I will do now just to prove that that is the case. So I'll give it a number of detections here. So don't worry about the lamp for this. This is now no longer pretending to be a chain. I'm just using it to generate some counts. You can see that the angle of the product detection curve is changing. So what we normally expect to see is a sawtooth kind of wave, and what we've got is a bit of logic running in the SIG 200 where it counts up to 100 for a batch, and when we've produced 100 products, whatever they may be, we then reset the batch count to 0 and we count up again. You see I've really slowed down the count sequence there, and you can see that the curve has significantly changed in terms of its angle and how fast it's going up. And I'll just pop that back into demo mode and I'll explain what this graph is attempting to show. So the IMC Count 3 is actually another version of this demo case that's somewhere else in the country that's connected, and it's in a different state. So it's also in demo mode, but the speed of the flashing of the lamp, or the number of times per minute that the lamp goes green, is less. It's about half actually. Now what we're trying to show here, and hopefully this comes through, is that just because we're saying that these are demo cases, these could quite easily be two machines within a factory or within two separate factories in the country, mapping their data to a cloud-based platform whereby at a glance the efficiencies manager or somebody who's in charge of keeping an eye on how well things are running could see not only at a glance that IMC Count 3 or machine number 3 is running more slowly and producing less batches per hour than IMC Count 2. But it can also see at a glance, if they're sitting here and they've just logged on for a second, that they've just literally had a major glitch on IMC Count 2. And in addition to that, you can go back and view this data historically. So any glitches can be easily picked up. You might also be wondering what the button IMC Count 2 is. Well, that's just a little test button, and what that allows us to do is to send a signal from the cloud and down into the demo case. So at the moment it's not actually connected to do anything worthwhile, it's just to prove that the signal can go back. But it could be used for something like teaching in of a sensor, or passing some sort of message from a cloud-based platform such as this to the machinery. If you chose to. Now obviously that would have to be locked down and password protected to make sure that no one was doing stuff they shouldn't be doing, but it's a very useful feature to know that the TDC within the demo case can actually receive signals from the cloud as well as passing them up to the cloud. Fantastic. But development's all well and good, but now let's see what would happen when we want to use this in a real world application in a platform that you can get hold of right now. So we're in the AWS cloud now. If I just subscribe to the topic that we've defined in the Node-RED flow, straight away you can see we start to get information up from the case, and we've paid particular attention to the receiver level from the W16 and the quality of run, which you can see here are 98 and 97. What I'm going to do is I'm going to introduce the plastic window in front of the reflector again, and we should see that those values will drop next time the data is uploaded, which will be within the next few seconds. There you go, straight away. 70 receiver level, 73 quality of run. The quality of run will continue to drop until it plateaus, and then what we can see if I remove the plastic window again, let's say we've sent an alarm to the maintenance department and they've gone along, they've established that there was some soiling on the screen and they've cleaned it, and we're going to remove that marking out and everything's back to where it should be. Receiver level shoots straight back up, and the quality of run starts to track back up as well, so the algorithm is doing its job there. And you can see we've got plenty of data being provided, lots and lots of lines of data. You'll see the shift production values going up, and it's all very useful stuff. So as promised, here we can see the AWS cloud with some analytics based on the data that we've uploaded. So this graph, for example, would be one way of viewing it. So if in a production environment you wanted to see for which temperatures of the environment you got the most throughput on your machinery, this might be one way to do that. So you could see that for certain temperature variables or values, you would see increased throughput on your machinery, and you would then be able to start looking and cross-reference as to why that may be. Different ways to view the kind of data that we're looking at though. So here we can see, depending on the temperature, let's just put that by in order of the temperature, you can see spikes at certain temperatures. So these reflect what we were seeing before. This tall one here for a temperature of 35.2, you would get many more instances of the count. And at the end of the day, how you interpret the data is entirely up to you, but what we're showing here is that getting the data into the cloud, whether it be AWS, whether it be Azure, whether it be something provided by SICK, it's not hard to do, and that's the important thing to take away from this. Well, thank you for your attention. Ordinarily in the webinar we'd take questions and try and provide some answers now, but clearly as this is a recording we can't do that. If you do have any questions at all, or you'd like to arrange some sort of visit or communication between ourselves, please do drop us a line at info@sick.co.uk or give us a call at our main office on 01727 831121. Thank you very much for watching.